What we're going to do in this video is talk about something called formal charge. And as we'll see, formal charge is a tool that we chemists can use in order to think about which of the valid Lewis diagrams for a molecule might contribute more to a resonance hybrid than others. And what we're going to focus on is sulfuric acid. So sulfuric acid actually has 4 legitimate resonance structures, 4 legitimate Lewis diagrams that you could draw of sulfuric acid. And I have 2 of them right over here. But what we're going to do is use these to practice calculating formal charge and then begin to think about what that tells us about the various resonance structures and which ones might contribute more to the resonance hybrid than others. So first of all, I will introduce a definition of formal charge. And it's really a calculation for calculating the formal charge on any given atom. So I'm going to define it as the number of valence electrons in free neutral atom, I'll just say in the free atom, and then minus the number of valence electrons, I would say, in the structure allocated to bonded atom. And I'm going to define what it means to be allocated in a second. Allocated to bonded atom. And so what does it mean, the number of valence electrons allocated to bonded atom? Well, the way we think about it is, let's just pick this oxygen up here. So what we imagine the valence electrons allocated to the bonded atom, it is going to be the lone pair electrons. Make a little thing like that. So it's going to be the number of lone pair electrons plus 1/2 of the number of shared electrons. So for example, this oxygen that I just circled, your number of lone pair electrons is 2, 4, 6, and then half of the shared electrons. There's 2 electrons that are shared in this covalent bond, so it gets half of them. So you could imagine an electron right over there on that half. So that gives us a total of 7 valence electrons allocated to the bonded atom in this circumstance. So what would be the formal charge of this oxygen atom in this sulfuric acid molecule? Well, the number of valence electrons in a free atom, we've looked at oxygen many times. A free neutral oxygen is going to have 6 valence electrons. And then the number of valence electrons allocated to the bonded atom, 2, 4, 6, 7. We just calculated that, minus 7. So that gives us a formal charge of -1. And one way to conceptualize formal charge is that within this molecule, this oxygen has 1 more electron hanging around it on average than a free neutral oxygen atom. Now, by the same logic, we could say the formal charge of this oxygen atom down here is also going to be -1. So this is also going to have a formal charge of -1. Now, what about this oxygen right over here? And notice I'm taking half of their bonds into the picture. Well, a neutral free oxygen atom has 6 valence electrons. And the valence electrons allocated to this oxygen atom in this molecule are 2, 4. So 4 lone pair electrons. And then half of this bond, so 5. And then half of this bond, 6. So it has 6 valence electrons allocated to the bonded oxygen here. So this has a formal charge of 0. By the same logic, this oxygen over here has a formal charge of 0. And then what about the hydrogens? Well, this hydrogen right over here, a free neutral hydrogen would have 1 valence electron. And then the number of valence electrons allocated to this hydrogen, it has no lone pair electrons. And if you give it half of this bond, that's just 1 electron right over there. So it has a formal charge of 0. And by the same logic, this one over here also has a formal charge of 0. And then last but not least, let's think about the central sulfur. A free neutral sulfur atom will have 6 valence electrons. Now this one, if we count the number of valence electrons allocated to this bonded sulfur, it has no lone pair electrons. But if we give it half of each of these bonds, 1, 2, 3, 4, so 6 minus 4 gets us to +2. So we've now calculated the formal charge on everything. These oxygens, the top and bottom oxygen, have formal charges of -1, and the central sulfur has a formal charge of +2. And a good check on formal charge is when you add up all the formal charges, it should equal the charge on the entire molecule. And this adds up because +2 minus 1 is 0, and this entire molecule is indeed neutral. But now let's calculate the formal charge here. This is another legitimate resonance structure for sulfuric acid. And actually, I encourage you to pause this video. Try to work through it on your own now that you have a little bit of practice looking at formal charge. All right, let's do this together. Let's look at this oxygen up here. So neutral oxygen would have 6 valence electrons in a free atom. And this one, the number allocated to it, 2, 4, and then 5, 6. So 6 minus 6 is 0. So by the same logic, this one also has a formal charge of 0. These oxygens here, they have the exact same configuration of these oxygens on the left. So they are also going to have a formal charge of 0. The hydrogens are in the exact same configuration as well. So they also have a formal charge of 0. And then what about our central sulfur right over here? So a neutral free sulfur atom is going to have 6 valence electrons. And the number of valence electrons allocated to this, we have no electrons in lone pairs. But if we take half of the bonds, we have 1, 2, 3, 4, 5, 6. So minus 6 is equal to 0. So in this version of sulfuric acid, this resonance structure, you actually have no atoms with non-zero formal charge. And as we'll see in future videos, the more that your individual atoms have formal charges closer to 0, the more that resonance structure will contribute to the resonance hybrid. So if we were just looking at these two, we would say that this one over here is going to contribute more to the resonance hybrid than the one on the left, because the one on the left has more individual atoms with formal charge that are away from 0. You have 2 atoms that have a -1 formal charge, and you have 1 atom that has a +2. Here, they're all 0.